הרצאה מאוד לא קוהרנטית בשתי צדדים. לשיקולך, מה שנוח.
אולי אני עושה באנגלית. יכול להפנות אנשים ליוטיוב, נראה איך יצא. The social media and democracy, it's joint work with Yuval and Hillman, who you know. Okay, so this is about how information influences voters, voting for some candidate or some policy. And traditionally, when we think about voters getting information, we think of them as getting public information through mass media, things like political advertising, endorsements, in newspapers and on billboards, and this sort of thing. But increasingly, in our modern day and age, voters or people in general get information through their social media networks. Some of this information is political information. People always tell me when people don't go on Facebook for politics. And so here's the paper that I'm citing here is a paper by Hunt Alcott and some co-authors where they do, I just feel like this paper, they do an experiment where they pay people to stop using Facebook. I think for a month or two, I don't remember. And then they look at what are the significant effects after they stop paying them for it. One of the effects is people have become happier, not being allowed to use Facebook. But another one of the significant effects is that people are less well informed about political events. And so even though people don't go on Facebook to get political news, they do get a lot of political news, even unbeknownst to them. Okay, that's just Facebook. Of course, on Twitter, people do go on Twitter to get some news about politics. And so how do they get this news on Twitter or on Facebook? So it's all automatic, right? So there are algorithms that basically, when you go on Facebook or you go on Twitter, there are algorithms that select what information you see, what the order is, and also what you see. You don't see everybody's posts. You don't see all the tweets from the people you follow.
It's like a church.
Yeah, it's 11:06. This is the time for mass. Okay, so for example, on Facebook, there's the newsfeed algorithm, which uses a lot of data to tailor the order with which you see your newsfeed, like whose posts you see and what you don't see. Twitter also, it amplifies certain tweets and doesn't amplify others. It gets more people to see certain tweets and not others. And also they do some sort of censoring, like they have warning labels, and maybe they ban certain users on Twitter. Yeah, this might be changing now with the new ownership, but that's at least how it's been done.
The newsfeed is distinct from the general.
No, so I think that's called your feed, your news feed. I think that's just the name of the algorithm that selects your feed. And so there's some empirical evidence that these algorithms that choose how to order the information that you see or what tweets to amplify have some political biases. It's, for example, this paper, the second paper here, the Gradwohl paper, basically they look at Twitter and they try to categorize different tweets by their political leanings, left, extreme right, or moderate. And they look at how tweets have been spread, which tweets have been amplified compared to others. And they do find evidence of some bias. I don't remember the direction, but there is some bias on there. And then he does some similar experiment on Facebook and also detects a certain bias in these algorithms. Because of these sorts of things, there's quite a bit of a discourse about, what are the effects of these biases? What is the influence that social media might have on politics? Because it has some bias.
It's not based on the preferences of the users.
Maybe that's not based on the truth. Maybe that, you have one tweet on the left, one tweet on the right, and the one on the right gets much broader amplification than the one on the left. Something like that.
It's based on how many people at this stage are watching it, or how much time they spend.
Yeah. So in the empirical papers, they do control for these sorts of things. Okay, so I'm not an expert on this, but presumably they would have control for this. Okay, so because of the effects, the prevalence of social media and news information, this has become, it's quite important to look at the biases in these algorithms. And how they influence democracy in general. So this is kind of our motivating setup. Basically, we're interested in the question of what are the effects of social media persuasion on voting outcomes on democracy. And that's the general question. And we look at it in particular, a very specific framework. We look at this in the theoretical framework of Condorcet's jury theorem, which very roughly says that when voters are not perfectly informed, they only have some imperfect information, then majority voting, when you have enough voters, will lead to the correct outcome with high probability. Okay, and the more voters you have, the more likely you are to aggregate the information correctly and reach the correct outcome, the thing that is in fact socially optimal. Okay, and this, why it's useful, why it's interesting, is in some way it demonstrates the merit of democracy. And why is majority voting good compared to, say, a dictatorship? And basically, we take this framework and we look at voters who have this important information, like in Condorcet's theorem, but in addition, they get some more information, messages from a social media platform. Okay, we give them some additional information. Okay, so the way this is going to work is there's going to be some platform designer. Okay, think of platform designer as Elon Musk. He commits to some sort of a messaging mechanism, how messages get distributed in the network. And this is kind of supposed to model the algorithms, like Facebook's newsfeed algorithm or Twitter's amplification algorithm, that determine how information gets ordered and selected. But of course, the designer might not be completely indifferent between outcomes, and so he might have a preference for one outcome over the other, which might be different from the socially optimal outcome. And the question is, in this framework, when voters get additional information from a possibly interested social media designer, does Condorcet's theorem still hold? Does majority voting still lead to the socially optimal outcome with high probability? Yeah, so that's the question. And here's the main conclusion. So I'll just, no suspense. When voters get additional information from an interested social media platform, then the platform has a way to design the mechanism scheme, the messaging scheme in such a way that the outcome is always the one that the designer prefers, not the socially optimal. Okay, that's the punchline. We view this as overturning Condorcet's jury theorem, and so undermining this argument in favor of democracy.
This conclusion is very much moderate.
Dependent.
Huh?
Right.
Which conclusion? That it overturns
That it can
Condorcet's
do it.
theorem? The main conclusion,
Yeah.
I mean, that when you give voters additional information, then majority voting no longer leads to the correct outcome.
But the answer
So-
it depends.
Depends on what.
Many things. So the answer is not yes or no. Your answer is yes. Follow?
Yeah, of course, I'm gonna have a model, right, which is gonna be an extension of Condorcet's model. And you can argue that Condorcet's conclusion is also, yes, it depends on the model. Sure, he had a particular model showing that democracy is great. Sure, give me a different model. Maybe it's not. And so I'm taking the model that says, a particular model that says democracy, majority voting by voters leads to the correct outcome. I'm telling you, well, if you have additional information, then that might no longer be true. Okay, there are going to be two features to our study. Okay, two things that drive the result, two assumptions in our model. One of them is that the designer can credibly commit to how messages are generated. Okay, it's not cheap talk. He can't just send arbitrary messages. Before he gets any information, before people post the tweets, he decides how he's going to send out the tweets, and then the tweets start arriving, and he's committed to this mechanism. Think of it as the algorithm is set up, and then people start posting tweets on Twitter, and the algorithm sends them out or amplifies certain ones and not others. Okay, so the designer would set up some preferences of the outcome, so he might commit to a biased way of spreading these messages. He might commit to a biased mechanism. And of course, voters are, in our model, going to be aware that the mechanism is biased. He's not going to be fooling them.
It's like in the case of Bayesian
This is going
persuasion,
to be a Bayesian persuasion model.
where the decision to make is binary, 0 or 1, go to this party or this party.
Yeah, that's what it is. It's going to be a Bayesian persuasion model. Exactly.
Can increase the.
Exactly. Okay, so that's one assumption that we make. Another assumption is that we're going to think of this as being a large election. A lot of people actually want to have a continuum of voters. And voters, in this sense, their vote has no impact. Their particular vote is negligible. Okay, so in particular, we're going to think of voters as voting for the alternative that they think is more likely to be correct. Okay, they're not going to be conditioning on being pivotal in the election or anything like that, because they're not going to be pivotal.
Why does it matter?
Why does it matter that they don't condition on being pivotal? And so I'll say a few words about that when I talk about the related literature. Okay, it changes the whole dynamic of the effect of messages.
Okay. It wouldn't matter if there were only two alternatives, right?
No, it doesn't matter if I mean. So in our setup, we're gonna have a continuum of voters, so they're not gonna be pivotal, but if you had a finite number of voters. Right, then their effect is pivotal, right, there's a chance that their vote might change the outcome. And if you think about what happens in an equilibrium in this sense, then basically they condition on this event of being pivotal. And they vote basically under the assumption that they're pivotal in this election.
What I'm saying is, suppose that only two of them appears.
Yeah,
So there's no strategic considerations, right? I'm wrong?
there are still strategic considerations
Okay.
because of what the designer can do. Okay, so these are the two features, and under these features, we're going to characterize what are the direct effects of this kind of social media persuasion on voting outcomes. Okay, so before I go into the model or anything, I want to do like an example to kind of preview what the model looks like and what the forces are, and what the results are going to look like. Yeah, so it's going to be a simple example. We have two alternatives, A or B. I think of them, one of them is better, with a socially optimal one. And we don't know which one it is. There's a voter. This voter is uncertain about which of the two is better, but he has some limited information that supports one of the alternatives. Okay, so let's say this information is 55% accurate.
Better or not better, it's individual.
Better or not better is
Objective.
objectively better. It's a socially optimal.
So
There
what,
is a
all
correct-
the population had all the information they.
This is the one that everybody would choose. Okay, so what does this mean? So we have our voter here. Let's say this voter has some information supporting alternative A. So what that means is he believes there's a 55% chance that A is better, a 45% chance that B is better. Okay, similarly.
So assuming a prior rate.
Yeah, it's not a 50-50 prior. Okay, so
That's a.
it's not gonna be a crucial assumption for the results, but in this example, it's yes. Okay, so he thinks a 55% chance A is better, 45% chance B is better. If he has, symmetric, he has information supporting B, then it's the other way around. Okay, he has 55% certainty that B is better. Okay, so if he votes based on this information, then obviously he'll make the right choice to choose the correct outcome, probability 55%. Okay, so now it's supposed to be a bunch of voters, each one of them has some information supporting one of the two alternatives. Okay, each one gets the correct information, the probability 55%, right? Their information is 55% accurate. And they're gonna vote according to the information that they have. And so Condorcet's theorem says that majority voting is going to lead to the choice of the better alternative with near certainty. If you have the more voters you have, the closer you get to probability one of getting the right outcome. Okay, so we love large numbers. And Condorcet's theorem actually says something stronger. It says that adding just another voter increases the probability. That we care even about the limiting case. You have an infinite number of voters, probability one, you get the right outcome. Okay, so now let's introduce an information designer. And this is a social media platform. It's going to send additional messages to the voters. Here's our social designer. Let's suppose that our social designer wants the outcome A. Doesn't care about the socially optimal one, which is better, doesn't matter, just wants the outcome A.
Maybe it's a technical question, but how do you overcome the technicality that there is some rule, the Condorcet rule is the majority, how do you compute the majority?
What do you mean?
When you have a continuum, some of them, you have a subset of them, voters who vote A and subset B, but these are set or not measurable.
You assume majority.
Well, I'm going to think the voters are the interval 0, 1. Basically, I'm going to look at the probability that each voter is going to vote for A and the probability each voter is going to vote for B. They're symmetric. And then I ask, is this probability greater than a half? If it's greater than a half, then I'm going to say that the majority voted for A. If it's less than a half, then the majority didn't vote for A. Well, yeah, it's a continuum. So I think this is a fair translation of the Condorcet rule.
Okay. What is it was correct? It's not only good extent.
This is what?
This is not only good sense. The probability is not well defined.
The probability is the probability? Sure, it is. It's a number, right?
The probability that 60% or more will vote for A is not well defined.
the probability that 60% or more will vote for A.
There's no distribution. No, he said that the rule is not based on the action, but.
I'm just looking at the probability that a particular voter votes for A,
Fine,
okay? If that and they're all gonna be symmetric.
yes.
Okay, so if that probability is greater than 50%, I'm gonna say the outcome is A. If that probability is less than 50%, I'm gonna say the outcome is B.
It is a different proposition than saying that more than half will vote for A, half will vote for A. This is a different proposition mathematically.
Okay, but this is, I think, how we would translate Condorcet's rule to a continuum of voters. I don't see a different way of doing that.
The problem is measurability, not that way. The important for you, but this is not well defined. The question, the measure of the voters voting for any alternative is not well defined.
Okay. But why should I care? I mean, if I'm saying that the rule is based on the probability. So I agree, so yes, it's not measurable, okay? Okay. Sure, take that comment. Okay, so here's our designer. The designer said wants the outcome to be a particular outcome, say A. And so the way this works, the designer is going to get some information eventually about which state actually is better. This is the state. Okay, the state of the world is which outcome is actually better. But before he learns the state, he has to commit to how he's going to send messages to the voters based on the realized state. Okay, this is committing to the algorithm before the tweets actually start coming in.
How does the designer learn?
How does the designer learn?
Yes.
So you can think about him as not learning, that's just designing the algorithm that's a function from the realized state to the messages. Okay.
So what does the first line mean?
So this is a different way of saying that he doesn't learn, that he just commits to an algorithm.
Doesn't learn.
What?
Doesn't learn.
So you can think about it two ways. You can think of him as committing to a mechanism, to the function from the state to messages. And then it doesn't matter what he learned or not, he's already committed to that function. Okay? Or you can think about him as kind of the way I intuitively think about the Bayesian persuasion framework is, yes, I'm committing before I learn the true state, then I learn the state and I send a message and I'm committed to sending it in a particular way.
So this is a version of Twitter where Twitter sends the tweets rather than the users of Twitter.
No, Twitter commits to the algorithm. Twitter commits to the algorithm, then the tweets come in, and then how the tweets get distributed.
But I didn't get the answer to your question. It seems that the designer has to know the state.
The designer has to know why. No, the
That's what you
designer.
said.
Again, so there are two ways of thinking about it. Think about the designer never learning the state, but committing to a function from the state to the messages. He just committed to the function. The state gets realized, and the voters get the message according to this function.
State gets realized, but nobody knows it. And still the function is executed.
It's Bayesian persuasion. And I'm not even going to go here.
No, but as far as I remember, Bayesian persuasion, somebody knows the state, or at least has some information.
But they learn the state after they committed to the mechanism.
Right.
That's the point. That's what I'm saying. The designer really learned which alternative is better, but before he learns, he commits to the mechanism.
What I'm saying is, it seems to me that he has to know eventually know the state, while the public does not.
It doesn't matter what the designer knows or not, right? Does Elon Musk know the state? I don't know. He has an algorithm that figures out how to distribute the tweets that people send on Twitter.
But can he?
Does he learn all the tweets? Maybe, I don't know.
Can he make the algorithm contingent on the unknown state? I don't understand this.
He commits to a mechanism which is a function from the state to messages. It's a function from the state to the messages.
You commit to making some forensics test. It depends on real estate.
Commit to an experiment. Commit to an experiment. And eventually I see the outcome of the experiment. So the outcome depends on the true state. Does the drug work or not? Do I know what it works? Maybe I do, maybe I don't. But I committed to an experiment and I see the outcome of the experiment.
So what is this function? What does it stand for? Can you get an example? Any idea for this function represents?
You're talking about in this particular model or in general, what is state persuasion?
From state to message.
I think I understand what it's not clear.
What's
It's a
that?
function of the state, but the state is random, and also the result is random.
Right.
You can see different results. The
Yeah.
state is unknown, but it's a function of the state. You don't know what you will see, and it's with noise. You cannot conclude what is the state if you see what the designer do.
But how can you implement a mechanism that depends on the state without being able to know what the state
It's the
is?
same. You run some statistics that it depends on the state. The result of the
So you
statistics.
have information that the public is not
All the
Experiment, I don't know the state. I design an experiment. The outcome of the experiment depends on what the state is, but I don't have to know the state to design the experiment.
But when you design an experiment, nature knows the state, and
Nature.
then
knows
nature.
the nature determines the state.
Exactly. And if I tweet something, and Twitter needs to decide what to do with my tweet, whether to amplify it or not.
Mhm.
According to this, Twitter should know the state to decide whether my tweet should be amplified or not.
Why? You can write a right-wing tweet or a left-wing tweet, okay? And I'm committed to an algorithm that the right-wing tweets I amplify more than the left-wing tweets. Now, it could be that if the state is left, then more left-wing tweets come in. And so maybe they get amplified,
So
because
this,
there aren't many right-wing tweets.
so this is what I think is missing. You decide on the algorithm, which is independent of the state, and then as a function of the state, the tweets are the one that's
Yes, that's the messages that they're the
Which are
outcome of the mechanism.
outside of Twitter, outside of the Twitter designer. He's not controlling the.
Not controlling the state, of
tweets.
course.
Yeah, no, he's not controlling the tweets.
What my objection is that it seems that the designer has access to information that the public does not have. If you can execute an experiment, why can't the public execute the same experiment, get some information about the risk? He has some knowledge advantage, that's what it seems to me.
So the public here is the voters that are receiving tweets, right, that are receiving messages. Then there's somebody else, you can think of them as having more information, you can think of them as just being able to commit to a mechanism. A mapping from states.
But if that mechanism is executed
Yeah,
before people vote,
yeah,
then at that point, we have information that the public does not have.
I don't understand why. Think about the example of an experiment, right? If I run an experiment,
I can run the experiment too. Why don't I? The public wants to know the state. Why can't
because you are not as rich as Elon Musk. It's an informational asynchronous, right? If everybody has the same information, sure, then we have nothing to talk about. Then we shouldn't go on Twitter or Facebook, I already know everything.
Okay, but then again, he has some knowledge that the public does not have.
Resource.
Again, it's not that you might have to think of it and having knowledge, but he's being committed to a mechanism, or you think of them as being able to commit to a mechanism that turns some knowledge which will get realized by nature into some messages.
And at that point, he will be more knowledgeable than the public.
He gave the algorithm, maybe that's people coming in, but not he gave the designer who designed the rule.
Think about Musk, who has superior knowledge and intelligence. Looking down.
No, think about Musk who has superior money, who can program a mechanism that will map states to messages. Okay, he doesn't know more than us, but he has the ability to commit to a mechanism.
Okay, what's the end of the?
The voter listens to tweets. The voter reads the tweets, gets the messages. The voter also has the ability, then let every voter get all the information and you're done. You can all go home. Nobody should be on Twitter.
This is why everyone is on Twitter. They all know everything.
They all know
need to
everything.
spread it.
Okay, so that's the framework. Let's say that the designer, the mechanism, we're gonna restrict the mechanism to being a binary mechanism. Means you can send one of two messages. And we're gonna see this without loss of generality. You can send either the message that A is better or the message that B is better. Okay, he doesn't have to tell the truth, he just has to pre-commit to how he maps states to messages. Right, so this is the mechanism that it commits to, it's a function of the state. And the important thing is the voters know what the mechanism is. This is exactly the Bayesian persuasion framework.
But this is not real.
What?
This is not real.
This is not Twitter,
How do you look at Twitter?
this is the model of Twitter.
It's about
The tweets are the messages, the tweets that are sent by, so look, if you want to do a mapping to Twitter, so think about the realized state is what generates different tweets by different users. Okay, some are left, some are right. And now what you do with the different left and right tweets, that's what the mechanism does. Okay, so if the state is A, then maybe you have more left-wing tweets. If the state is B, then maybe you have more right-wing tweets. And the question is, how do you pass on those tweets? Okay, but before you decide on the mechanism, you don't know whether you're going to have more left-wing, more right-wing tweets to pass on and to amplify. Okay, so maybe there's in this is it's a model, right? So it's a state that maps the message. If you think about the state as mapping to a bunch of tweets, and the collection of tweets differs in the two states, and the question is how you pass that on to the voter.
voters get all the same message.
So I'll be specific about the concern. They're not going to get the same message. They're going to get a conditionally independent draw from them.
But the message depends only on the two state and not on the action of the voter.
The voters don't act afterwards.
At that point, all the voters look the same.
They look the same. They might have gotten different messages, but the distribution over what information they have is the same for every voter.
They got different messages from what? From the mechanism?
So let me give
or
you a couple slides, all right? I'll be specific about what the setup is.
Well, the mechanism is the same message.
What?
No,
It's not the
mechanism
same.
sends different messages.
Could send different messages to different voters, but with the same method.
At the time where the mechanism decides which message to send, the voters all look the same to the mechanism.
To the mechanism, yes, they look the same. Okay, so here's just a simple example of what can the designer do. So one thing you can do is if the state is A, it could be an identity map, right? And state A to reveal that the state is A, and state B to reveal that the state is B. Okay, that would be one thing that the mechanism designer could commit to. And in this case, the voter will know, having received the message from the designer, will know what the state is. Okay, the one-to-one method. Okay, but maybe this isn't great for the designer, because remember, he wants the outcome A. He doesn't want the outcome B. So maybe he says, okay, I'll just always tell them that A is better, regardless of the state. Because remember, the voter knows the mechanism that the designer is using. So if he knows that the designer is always sending the message in favor of A, then he actually learns nothing new from this message. Okay, so this is an uninformative mechanism. So just stay with his original information. Okay, so can the designer do something that's better than revealing the truth or not revealing anything? So here's a kind of a standard mechanism of persuasion that you could use. If the state is A, then he'll commit to revealing that the state actually is A. If the state is B, then he'll flip a coin. And 30% of the time he'll say that B is better, and 70% of the time he'll say that A is better. And there's one thing you should do. Commit to this mechanism. Now, how does the voter react to getting a message from this designer? Well, it depends on what the voter's initial information was. Okay, did he start with information supporting A or B? So let's suppose that so first of all, if he gets the message that B is better, then he does know for sure that the state is B. Right? Because the only time that this message is sent is in state B. So then he's sure. Okay, then he has learned that the state is B. Okay. But if he gets the message that A is better, then he doesn't know if the state is A and he got that message, or if the state is B and he got the 70% end of that message. Right? He doesn't know which one it is. So he has to update based on this information and his prior information. So if we had information supporting A, then now he calculates his posterior on the state A being actually better given that he got this message. Okay, this turns out to be 64% and his own information and the message that he got that A is better. Okay, so you start with the prior 55% and his posterior now is 64%. Okay, it's increased.
No.
Okay, so this is if the voter has information supporting A. If the voter has information supporting B, then his prior is different. His prior is 45%, that A is better, but he still gets information supporting A. You can calculate his posterior, and it's now 54%. Okay, so he started with either 55 or 45, and now he's upped his belief that A is the right statement. Okay, given this message, not to 100%, okay, but higher than what it was. Okay, so depending on what information they had, right, they update their belief either to 54% or to 64%. Okay, so what is the effect of designer's message on voting outcomes? Well, if the guy got the message that B is better, then he knows for sure that B is the better outcome, so he'll vote for B. If he got the message that A is better, then notice that regardless of what his prior information was, he's still in belief that B is better, that A is better, with probability above a half. Then, assuming that he votes for the outcome he thinks is more likely, either case, he'll vote for A, regardless of his prior information. Okay, so that's the effect on one voter. What happens if we have many voters? Okay, so we're going to think about voters. Everybody knows the voters mechanism. And each one is going to get a conditionally independent message according to this mechanism. Okay, they don't all get the same message. If it's one mechanism and everybody gets the same message, then I'll think of that as public persuasion. That's more like everybody reads the same billboard or everybody reads the same article in the newspaper. But social media is individual. Okay, and the way that I want to model it is that each person gets an individual private draw from the distribution of the mechanism that the designer chose. Okay, so here are our voters. Okay, here's our mechanism designer, state A and state B. In state A, everybody gets the message that A is better, the independent draw. In state B, each one gets an independent draw of this message or that message. Okay, with those probabilities. Okay, so how do they vote? So remember that voters who got the message A is better vote for A, and voters who got the message B is better vote for B. Okay, so in state A, all voters get the message A is better, and they vote for A. Right, in state A, everybody gets that message, they all vote for A. Okay, with probability 1, A is the chosen outcome. What happens? So in particular, a majority votes for A, the correct outcome. Okay, each voter votes with probability more than 50%. Okay, so we avoid the measurability problem. What happens in state B? Well, in state B, remember, each voter gets a 30-70 mix of B and A, right? In particular, 30% of voters get the message B is better, and 70% get the message A is better. Right? Or each voter with 30% probability gets that message, and 70% probability gets the other message. So if you think about what happens with the majority, right? The majority votes for A. This is the incorrect outcome. The state is B. Okay, in particular. So this overturns Condorcet's theorem. But everybody always, regardless of the state, regardless of their initial information, you get each voter voting for A with probability greater than half. Okay, and so regardless of the state, the outcome is A. Okay, this is also, not only is it worse for a majority, this is also worse than a single voter making the decision. If you just have a single voter making the decision, right, at least he gets it right with probability 55%. And here in state B, they never get it right.
No, you mean single voter persuaded by the design.
Yeah, this is even worse than a single voter persuaded by the design. I don't have that argument on the slide, but that's also true.
They should convene another social media and check if anyone got it.
If anyone, yeah, so if they talk to each other,
That's
right,
exactly
under this
what I
mechanism, then yes,
mean, probably.
with this particular mechanism.
No, you can introduce someone.
Yeah, so there are going to be other mechanisms where you're not going to be able to do that.
The such argument refers to a situation where the private messages are on the list. And here you have another message which is correct with 100%. So comparing these two different, the such argument is a comparison between two different setups.
I mean, I'm taking the Condorcet setup and I'm adding something to it.
Because the second term is about whether it's about the wisdom of the crowd.
Yeah.
But here you have this superior must knows the truth. So So he can manipulate the masses, but it's not about getting to the truth, because the truth is known.
I mean, so this is the same argument we had before. So Max doesn't know the truth, but he can use a mechanism that determines how messages are sent, right?
But he's the algorithm knows the truth. The truth is known.
The truth is that if the mechanism depends on the truth state.
The mechanism depends on the true state.
How can Elon Musk make a mechanism that depends on the truth state if he doesn't know the truth state? Who knows the truth state that the mechanism depends on?
Okay, I have 2 coins, okay? One of my coins is heads and tails, the other coin is heads and heads. I hold them behind my back. Okay, the mechanism is I flip the coin. You're gonna choose one at random and I'm gonna flip the coin. There's gonna be an outcome, right? Here's a mechanism where I can choose, right? Where I can change the probability. It depends on the state. You don't know the state, I don't know the state, I've mixed them up. I don't know which one is which. But still, the mechanism depends on the state, the outcome depends on the state.
Okay,
Like every scientific experiment has this feature.
so.
Right, there's some ground truths, we run an experiment. In order to define the ground, we don't know the ground truth when we run an experiment. Right, there's ground truth, we design an experiment, and there's outcome.
First, I must say that it's very nice. It's not the end of the story, but it's very nice to participate. And I must say that you could present this a little bit differently, which there is all this difficulty. By saying that the mechanism depends on the opinions of all the population. It will make exactly the same effect, in my opinion. So the mechanism doesn't have to be dependent on the specific state, but on the majority. And now Elon Musk has some interest, he doesn't want to expose the majority. So the mechanism depends on the majority, and he would like to convince us to take one side. And the same model can work.
Yeah, I like that.
So it will be much easier.
Yeah,
Now I don't understand what we got. After these messages, each voter has a posterior.
Mhm.
So you have some distribution, let's say the posterior is a point on the interval near one. So there are only finitely many possible posterior
for a fixed mechanism, yeah.
for this.
Yeah,
And each posterior has a different probability.
Yes.
And the average of these, now how does it work? What is the result of the jury?
the result is based on voting. So think about each voter, right? He's one of many posteriors.
Let's say
If
one
your
posterior
posterior is above 50%, then we're gonna think he is voting for A. And if it's below 50%, you're gonna vote for B.
posterior is above.
Yes, it's more likely to be correct, right? That's the voter's preference, is to vote for the outcome that's more likely to be correct. Okay?
So okay, now so the condenser rules that each posterior above 50% is A and below
Yes, exactly.
50% is B.
Exactly.
Okay, so that's
Okay, so in this example, the outcome is A. High probability, or the continuum of voters is always A. And so the question is, can the designer always?
Again, the same problem that you tried to avoid before, which was that the mechanism, the result of this vote depends on the posterior and not on the actions. You had this issue that the set of the voters who take each action is not measurable. Now the set of voters who take each posterior is not measurable.
So what I'm looking at is think about a particular voter. What's the probability that he favors A? What's the probability he favors B? Right? He has a bunch of posteriors. What's the probability that his posterior is above 50%? What's the probability that it's not? If the probability that his posterior is above 50% is greater than half, yeah, then we're going to say the outcome is in favor of A. If the probability that his posterior is less than 50% is greater than half, then we're going to say that the outcome of the mechanism of the vote is B.
So you take this half and split it by splitting
Yeah.
lemma and you put the things which are below half, you put them very close to zero, and the things that are above half, you put them slightly.
Well, that was
up.
this mechanism. But this isn't the best mechanism. Okay, but yes, but that's one thing you could do.
Okay.
Because that's a standard Bayesian persuasion mechanism, right? That's like the canonical one, just exactly that. Okay, so then the next question is, can
Why
the,
did this mechanism works? Okay.
well, here, it doesn't always work. I mean, you could always do this, but it doesn't always lead to the outcome A with probability 1.
You just convinced them.
Well, I convinced you that it's possible when the initial information of the voters had accuracy 55%. But for example, if each voter has perfect information, then obviously it's not possible. Doesn't matter what information, additional information I give you, if you're already 100% sure, you're not going to change your mind. Right? There's going to be some cutoff where it's no longer going to be possible to convince enough voters.
What is not so interesting in this example is that although all the population knows the interest of the designer, if they agree to listen to him, then don't have any way to escape for the result of voting for them.
Yeah.
It's very, very paradoxal and interesting.
Yeah, I like this too.
Yeah.
Okay, so this is the next thing, is we have to address, is there a limit to this possibility? Can you always overturn the election, do this? And the answer is no, it's going to depend on the accuracy of the voters' private information. They have 55% accuracy in this example, and we have a result that, at least in the simple setup, if the accuracy is below this square root of 2 over 1 over square root of 2, then this is possible. This sort of a mechanism is possible. If it's above that, then it doesn't matter what the mechanism is, you can't influence the outcome of the election. Okay, and the intuition, at least, is if the accuracy is if it's perfectly accurate, then you clearly can't do anything. But actually, it doesn't have to be perfectly accurate for not to be able to convince enough voters. Another thing we talk about in the paper is, can we say something about the properties of the optimal mechanisms for the designer? Okay, there are different mechanisms that achieve the same goal. Right, so the designer wants the outcome A. In the example, the mechanism was biased towards A. So what do I mean? I mean that the outcome of A happened more often. Right? In state A was the truth, but in state B, you always lied towards A. There's like bias towards A. I'm going to say this is a positive bias to this mechanism. Okay, in that example, there is another mechanism that is also able to lead to the outcome A with probability 1, which is biased actually towards B. Okay, then we might talk about that mechanism. And we have a result that says that sometimes the only way.
What do you mean? You just change the name,
If I change A and B, then the outcome will be B with probability 1. I'm talking about mechanisms that is.
It's a mechanism, you just change the message. A is B and B is A.
Okay, so right, so fine. So what I mean is that it's biased towards the state that the outcome. So change the name, fine. But obviously, there's going to be a formal definition here, right? It's the probability of leading to a posterior. Which direction do you move the posterior? You move it towards the outcome that the designer wants, or do you move it away from the outcome that people want? Do you more often move it towards A, or do you more often move the posterior towards B? So here I call A is better, the message that moves the posterior towards A, and B is better, the message that moves the posterior towards B. Okay, and if I change the name, I'm still going to leave it to be a positive bias. I'm still going to move the posterior closer towards A. Okay, but there's a mechanism that actually more often moves the posterior towards B than towards A, and still leads to the outcome, the correct outcome, the A outcome probability 1. And sometimes this is the only way to get the outcome A with probability 1. Sometimes the only way that the designer can get what he wants is to actually commit to a mechanism that more often shifts the prior towards B than towards A. Okay, so
What is the difference between the parameters in the two cases? I mean, what makes this
well, in the simple model where there's where all the voters are homogeneous, it depends on the accuracy of the signals.
So if it's higher for them?
Yeah, so here I told you that right, can you always change the outcome? So you can do this if the accuracy is less than root 2 over 2. If the accuracy is less than 2/3, smaller than this, then you can use both kinds of mechanisms. If it's between 2/3 and √2/2, you can only use these negatively biased mechanisms. It's the only way to get there. Okay, so in the simple model, that's the outcome. Okay, and this is kind of, we find this interesting because it's biased towards the opposite direction of the one that the designer actually wants. Okay, so if you think about, if you say the messages on Twitter are more left-leaning than right-leaning, that might, so this is pure conjecture, it might be that actually it's biased towards the right, even though more messages are on the left. That's one way of thinking about this. Why to me it seems counterintuitive. Okay, some other stuff we talk about in the paper is what if different voters have different accuracy levels to their information, and not everybody has the same accuracy level. We talk about some targeted information if the designer can commit to different mechanisms to different voters, like if you can differentiate whether you are a high accuracy voter or a low accuracy voter. And we also do this comparison between this private persuasion, where everybody gets a conditionally independent message from the mechanism, and public persuasion, where everybody gets the same realized message. So we think of this as a comparison between social media persuasion and traditional media persuasion. Okay, here's the outline, which probably we're not going to get to, but hopefully at least we get to the model. Just going to dive in. Okay, so I think maybe some of the questions were cleared up in the model, I hope. First, some related literature. Okay, so there's a Condorcet's theorem. I have another, the Feddersen and Pestendorfer paper is kind of a game theory version of Condorcet's theorem, where you have a finite number of voters and everybody conditions on being pivotal. Basically, they show that a similar kind of information aggregation result holds in that case as well. The paper is related to Bayesian persuasion, obviously. And there are papers that look at Bayesian persuasion as a way of
America and then Lomachenko and Ariel.
Yeah.
No,
it's okay. So America against because it's kind of the canonical paper here, and the closing on the other Lomachenko paper because it's Bayesian persuasion towards many receivers, so many voters. Because that's why those. Yeah, okay, I'm in Mashla and then so people have looked at Bayesian persuasion persuading voters, and there are basically two kinds. One is private persuasion, which is closer to what we do, where each person gets a different message. And there's public persuasion, which is when there's one mechanism, one message, and everybody gets to see that same message. Within the realm of private persuasion, the standard thing people have looked at is where the designer can commit to any mechanism that can also generate correlated messages to people, and also looked at the equilibrium in a finite number of voters and conditioned on being pivotal. Our setup is very different. Some of the results are similar, and some of them are different modeling assumptions.
is it crucial assumption you model that the population is continuous?
No, it's enough to say that voters vote sincerely. Voters vote according to their information and don't condition on being pivotal. Then everything works. Things are much easier to state because of the continuum. I don't have to say things like with high probability. Okay, so here's the model. Okay, we have these two policies A and B. We have a continuum of voters as to decide between them. There are two equally likely states of the world. Okay, so everything generalizes if you don't have a prior 50-50. Okay, things are just much easier when it's 50-50. Where the interpretation is that A is the better outcome, socially better outcome in state data A, and B is the socially better outcome in state data B. Each voter gets a symmetric binary signal. The realizations could be A or B. And the accuracy of the signal is Q, which means they get the realization A in state data A or B in state data B with probability Q. And Q is between 0.5 and 1. And we're going to assume that there are two kinds of signal accuracy. We have some fraction, a lambda fraction of the population has low signal accuracy, QL, and the rest have a high signal accuracy, QH.
The information is independent?
Conditionally independent. Given the state, it's independent. Okay, there's an information designer, D, can send them additional signals that depend on the state of the world. and you want to maximize the probability that policy A is chosen regardless of the state. And he commits to a binary signal, which is a function from theta, the state space, to a pair of messages. These weird frac A or B.
Could be A or B,
What?
could be just all plain A or B.
Well, because I have A and B and I have this A, right? A and B is also the signal that voters get. And then I have A and B that they get from the designer. They get two signal realizations. Okay, and those are different. Okay, and each voter gets a conditionally independent realization of S. Okay, the state is realized and everybody gets a conditionally independent realization. Okay, we're going to assume that the A message here is the one that moves the posterior towards A, and the B message is the one that moves the posterior towards theta B. That's how we just flip everything. Okay, the assumption that S is binary is without loss of generality. This is kind of a standard argument. Not quite standard, our setup is a little different, but the idea is because the state space is binary, it's often enough to have binary signal. And now we're also interested in the bias of a mechanism.
What do you mean by
That if there exists a mechanism that leads to the outcome desired by the designer, probability 1, then there exists a binary mechanism that does the same.
that's a proposition?
Yes. Okay, what's the bias? The bias is the weighted difference in the size of the lies in two directions. Okay, so there's a probability that in state theta B, the message A gets sent. That's a lie in the direction of A, right? A is the one that's supposed to move the fire towards A, towards theta A. This is a lie. And this is the lie in the opposite direction. So the bias is the difference between the two. So a positive bias is one where there's more lies in the direction of A. And a negative bias is one where lies are in the direction of B. Okay, so the metric signal is unbiased. And you lie with the same probability in both cases. Okay, so positive biases are more likely to lead to the realization A, and negative one to the realization B. In the canonical example in Bayesian persuasion, the optimal signal has positive bias. You think as the desired outcome as like the prosecutor convicting, the judge convicting, the person who's charged, or the standard Bayesian persuasion example, which is exactly what we have here. It's positively biased. Okay, in the one state you always tell the truth. It's the state that you want to influence in that direction. And in the other state, in the other direction, in the other state, you sometimes lie. Okay, we didn't make up this definition. It's based on a paper by McAnstow where he talks about bias in media in general. There's a particular instantiation of his definition. Okay, a strategy for a voter is a function that maps their two signal realizations into a distribution over votes for A or B. Yeah, I say a distribution over votes. I'm just going to assume that they're going to vote for the outcome they think is more likely, and we're going to assume that when they're indifferent, they're just going to vote for A. It just makes things easier, but the result doesn't depend. And the outcome is determined by majority, or think about whether a random voter is more likely to vote for A or for B. You're worried about the measurability issues. And ties are going to be decided in favor of A. Again, let's make things easy. Okay, but nothing depends on that. The main assumption is that voting is called in this literature sincere. So each voter votes for what they think is the best outcome given their own information. They don't condition on what others might be doing. In our case, it doesn't matter because conditioning on being pivotal is a zero probability event. But if you want to think about this model with a finite population, then it does matter.
Why? What other considerations are there? What's the considerations are there?
Well, if I know that I'm pivotal, then that tells me what information other people have done. Right? So you know this literature on strategic voting. Right? So for example, unanimity voting is not incentive, like voting sincerely in unanimity voting is not incentive compatible. In majority voting, it might also not be incentive compatible depending on the beliefs, on the prior, on the statements.
I don't understand. I only care about getting the outcome right.
Yeah.
So why would I vote for the other outcome?
No.
No, you
you
don't have
condition-
any else, for example.
You don't get, yeah,
You suppose that their signal don't go well with what you got.
so think about you're the time, you have to, if you're not the time breaking rule, then it doesn't matter what you vote, right? You're not the time breaking rule. So you have to vote based on the assumption that you are the time breaking rule. You're the time, but if you're the time breaking vote, then it tells you something about the information that other people have. And that information might be stronger than your own signal. So you might actually vote in the opposite direction of your signal.
Okay, but this doesn't happen with majority,
It doesn't happen, it also happens with majority.
right?
Sure, if the signal is not symmetric or the prior is not a half, or if you have an information designer that sends information that's not symmetric, then it also happens with majority. It could be that with majority voting, half the people have information supporting A and half have information supporting B. That tells me that the designer must have lied more in one direction than the other, and so I'd actually vote according to the opposite of what he wants me to vote. And this is actually the main driving force behind some of these other papers on private persuasion of voting. They show that if you have this kind of force, then basically there's no limits to what Bayesian persuasion can do. If you can take advantage of these kinds of pivotal voting events. Okay, so one way of interpreting sincere voting is that voters care about their vote. They get utility 1 when they vote for the policy that is the better one. And they get 0 if they vote for the policy that's worse. Or they care about the outcome. They get utility 1 if the better outcome, better policy is chosen, but they don't take into account the effects of pivotal voting. Okay, again, in our model, there's no pivotal voting because of the continuum, but if you think about a finite set of voters, then this is the assumption you would need to make our results go through in a finite model.
If they cared about the outcome, they would vote for people.
If they're not pivotal, they're never pivotal, then actually they don't care at all about how they vote. They never care at all about how they vote. They need some assumption if you have a continuum of voters about how voters vote.
If there are never people that they don't care about.
And it doesn't matter how they vote, right?
So their preferences are like.
They're irrelevant. So why do I think they should vote according to their information? So here are 2 stories. One is they get positive utility for voting according to the correct outcome. They care, right? Their utility depends on their action, their vote, not the outcome. Or continue to interpret this as voting, wanting the right outcome, but not taking into account how other players are voting.
They don't preference because they don't they cannot affect the outcome.
They cannot affect the outcome. That's true.
So their preferences over the outcome of the
So think about a finite. So that's what I'm saying. So here, the second one is not relevant in our model anyway, because it's never typical. But think about a finite voter model. Yeah, so that's why I have that on there, right? So people think about finite voter models. So not if they vote sincerely, right? They care about the outcome, but they don't. It's an assumption that behavioral types who don't take into account the other voters.
That's a pathology. If they vote sincerely, they mean that they don't vote sincerely. If they care about the outcomes and they could affect the outcome, they should have voted specifically and not in that other model where we find it.
Okay, I mean, I think about a model where I care about the outcome and I don't know what other people are doing and I'm ignorant. Okay, I don't even know if there are other people voting. Okay?
You think you may be the only person?
Maybe I'm the only person voting, so I'll vote according to my information. And that's sincere voting.
This model.
Okay. So just some quick observations. Suppose D doesn't send any information, designer. So suppose they only have their initial signal. And then there are some simple cases where the outcome is going to be A regardless because of our time breaking rule. So let's not go into this, okay? Because I think I'm just gonna go to some basic preliminaries and then state the result. Okay, I don't think we're gonna get to this level of detail. But here's an important observation: is that for every state and signal, doesn't matter what mechanism the designer commits to and what the realized state is, the outcome of the vote. Okay, the outcome being whether a voter votes is more likely to vote in favor of A or B. This is deterministic. Right? Either the probability is greater than a half that voters vote for A or it's not. And there's no probability of the outcome being A or B given the state. And the outcome is going to be deterministic. So basically, there are two cases. Either the designer can't manipulate the outcome, means that if the state is A, the outcome will always be A. And if the state is B, the outcome will always be B. He can't manipulate the outcome, or he can perfectly manipulate the outcome. That A is chosen in both states. Okay, there's a third one where he manipulates towards B in both states. Okay, but that's not an interesting one. Okay, the two interesting outcomes are where you can perfectly manipulate and where you can't perfectly manipulate. And then you can't manipulate at all. Okay, so those are the two cases. Okay, we're going to say that the signal is optimal if it can. If a particular signal does perfectly manipulate the outcome. Okay, and there might be multiple ways of doing this. Okay, so just some quick preliminaries. So again, let's think about, suppose the voter has 50-50 prior on state data A. Let's ignore for a second the information that he has. Now, any signal that the designer sends, right, you get a pair of messages, either A or B, it's going to induce a pair of posteriors, right? If the voter gets signal A, then his posterior is going to be this alpha. It's just going to condition on the signal A that he got. And if you got the message B, then his posterior is going to be beta. And these are the probabilities that A is the correct state, given the two messages that you could get. And actually, for any alpha and beta, okay, alpha being bigger than a half and beta being less than a half, there exists a unique signal S that generates these two priors. Okay, given these two posteriors. Given these two posteriors, you can backward and figure out what the signal is. Okay, with what probability you send each message in each state. Right, so 1-to-1 correspondence.
It's half, prior must be half too.
This is for the prior being a half. Prior is not a half, then you need beta less than the prior and alpha bigger than the prior. Because actually any informative signal, any signal that has some information, you can actually just identify it with a pair of posteriors, alpha beta, that it induces on prior 1/2. It's identical, talking about a signal S, or talking about the pair of posteriors that it induces. And actually, with this identification, we also have an enclosed form formula for the bias of signal as a function of the alpha and beta, okay, which is going to be helpful for us later on. So here's the main lemma, which simplifies our analysis a lot. Suppose we have a signal alpha prime beta prime that is optimal, meaning that the outcome is A in both states of the world under this signal. Then alpha beta, another signal, alpha beta is also optimal, where alpha can be less than alpha prime, but is either QL or exactly equal to QH. Alpha is either QL or QH. And beta is exactly one of these three: 0, 1 minus QH, or 1 minus QL. Basically, give me any optimal signal, and I can reduce alpha and reduce beta until it hits one of these points, QL, QH, or 0, 1 minus QH, 1 minus QL. Okay, and that signal will also be optimal.
And these sets are known.
Which sets?
Also.
That's an
The
accurate.
sets are, although we can take the maximum. Is there any Q which is one of these two and it's less than?
Well, I mean, for beta, right, 0 is yes. For this one, if alpha prime is less than QL, then no, then it's an empty set.
So the assumption here is what?
So the assumption, think about okay, right. So think about alpha. So alpha has to be bigger than QL.
Can you smaller?
Yeah. So if alpha is smaller than QL, then the mechanism is uninformative because you can't convince any voter.
What is Q? Q is the accurate.
QL is the accuracy of the low accuracy voter. If alpha is less than QL, then nobody's going to be convinced anyway, so it's an uninformative signal. Okay, so to be informative, alpha has to be bigger than QL. Otherwise, you're not giving any information, or at least any information towards A. So yes, I need to add that in here. Okay, here's the basic intuition.
When you say they have a 50-50 prior, that's actually the posterior after they got their private signal.
They start with a 50-50 prior, then they get a private signal of accuracy Q, so their posterior is either Q or 1 minus Q. Now they get another message from the designer. Q is the accuracy of their signal, of their independent, that's not from the decimal. That's like a 55-45. Okay, so the general intuition here is that if you have some signal alpha beta and you decrease alpha, so if you decrease your posterior, that means you can send out a message with higher probability, because the mean of the posteriors has to be a half. Right? So if you decrease one of the posteriors, you can send that message with high probability. So you more often send the A favorable realization A. And as long as you don't pass one of these lines, the QL or QH, then you're not changing the way any voter votes. Right? So a voter who voted according to, for example, if my belief was Q, okay, I had a Q probability of, or let's say I was 1 minus Q. I got a negative signal. I'm at 1 minus Q. And now I got a signal from the designer that has alpha, which is less than Q. Right? Then I'm not going to change my mind. I'm still below a half. But if I'm more than Q, then I'm going to change my mind. So as long as I decrease alpha or beta, but don't cross one of these 5 points, then no voter is going to change how they vote. You're never going to cross this 50% barrier on the posterior. Okay, so what this means is that if there's an optimal signal, then without loss of generality, there is an optimal signal where alpha is one of these two and beta is one of these three. Okay, basically we narrowed it down to 6 signals that are possibly optimal for the designer, and if none of them is optimal, then there is no optimal signal. And then you can't manipulate the election. And then basically we analyze each one of these 6. Okay, so these first two, QL0 and QH0, these are the standard Bayesian persuasion signals. The QL0 is the one where on message A, you get a posterior QL, you increase the belief with A. On message B, you decrease it to 0. And this is exactly the message that this is the mechanism that sends the message that B is better only in the state B. Right? And then your belief goes to 0. But you also have, for example, QL1 minus QL, this is a symmetric signal with accuracy QL. Just giving them another symmetric signal. And so for each one, we can talk about what is the bias of that signal, how voters vote, depending on what their signal accuracy is and what realization they got. And we can also calculate what the probability of a voter in state B. What's the probability that that voter votes for B or for A? And then we figure out if it's greater than a half or less than a half. Okay, so I think I'm gonna give you a few more slides of the result. So this is for a special case, just easier to state, where a lambda fraction of the population, the low accuracy voters, are completely uninformed. Okay, they get no signal, no individual signal. And then, because we have this tie-breaking rule that they vote for A, if there's a lot of them, then you're going to get the outcome A regardless, because a lot of these voters are just voting in favor of A. So there's this QNI of L function, which basically says that it doesn't matter if the number of voters, if QH is less than this, then you have enough of these uninformative voters to always get the outcome A. Okay, so we're going to focus on a more interesting case where this doesn't happen, where there is actually something to be done. Okay, so again, there's this line. I'll show you a picture in a second. So here's the proposition. So we have this fraction lambda of uninformative voters. So their Q is half. And these other guys are above this line where there's some action. Then if that accuracy is above this number, that number, then you can get no manipulation of the outcome. It's impossible for any mechanism to manipulate the outcome. If QH is less than this, then the designer can manipulate the outcome and get his desired outcome with probability 1. And in particular, you can do this using this unbiased signal. And the third point is if QH is in this interval between 2/3 and this Q upper bar, then all optimal signals have non-positive biases. Okay, well, it's true, this is one possible signal, but there are other ones, also ones that are positive. Because it's easier to see in the picture. So on the x-axis here, I have the fraction of uninformed voters. And on the y-axis, I have the accuracy of the informed voters. This red line is this QNI line. So if you have enough, if lambda is bigger to the right of this, then A is always chosen. There's no need for manipulation. Even an uninformative signal by the designer will lead to the outcome A. And this is the uninteresting case. Okay, so on the left of the line, you have the more interesting case where there's this cutoff line, Q over line, where above this, if the accuracy of the informed voters is too high, then the designer can't manipulate the outcome. If it's below this line, the outcomes can be manipulated. And in particular, in this triangle, above 2/3 and below this line, this is where only negatively biased or non-positive biased signals can manipulate the outcome. Okay, so optimal signals have non-positive bias. I'll give you some intuition for why you get non-positive bias. The intuition is actually pretty straightforward. So before voters get information from the designer, they're prepared to vote according to their initial realization. Right? If I got a realization A, then I'm prepared to vote for A, unless the designer tells me to give me strong evidence in favor of B. So what does the designer want to do? Well, he wants the people who got the B signal, he wants them to switch to A. But the people that got the A signal, he doesn't want them to switch to B, right? He wants to keep them voting for A. So how does he do this? Well, it has to be the case that if I get the B signal and now I get A from the voter, from the designer, A is stronger than B. Now I switch to A. On the other hand, if I'm an A voter and I got the B signal from the designer, B is weaker than A. That doesn't cause me to switch. Okay, so A has to be a stronger signal than B. Of course, the only way to do that is if B is realized with higher probability than A, because the mean of the posteriors has to be the prior. Okay, so that's why you get the negative bias in the signal. Okay, so that's that result. There's a particular case where it's a homogeneous population. Everybody has the same signal accuracy, and here there's just a specialization of the theorem, which is what we had in the beginning. If the signal accuracy is above this √2/2, there's no manipulation. If it's below √2/2, then there's perfect manipulation. And if it's in this interval, then we have the non-positive biases result. Okay, I think I want to skip ahead. Is there a way to? All right. So this is an extension to targeted signals. With targeted signals, the designer can more often manipulate the outcome, which is not surprising. There's a comparison between social media and traditional media. And these are two observations. One is with this kind of model that we have, the private persuasion. Either you get complete manipulation or you get no manipulation, depending on the accuracy of the signals. With a public signal, if everybody observes the same realization of the mechanism, you never get perfect manipulation, but you're always able to manipulate with some probability. So which is better depends on whether we can or cannot perfectly manipulate with private signals. That's what it comes down to. A public signal is everybody sees the same realization from the designer's mechanism, as opposed to private, which everybody gets a conditionally independent realization. Okay, and I'm just going to reiterate my takeaway message. So Condorcet's theorem says the majority vote leads to the socially optimal outcome, demonstrates the merit of democracy in some sense. And what we try to show is that when voters have additional information from an interested social media platform, then the platform can release information in such a way that the outcome is always the one the platform prefers, rather than socially optimal one, which we interpret as overturning Condorcet's theorem in this case and maybe undermining democracy. Yes.
One, I think you can overcome this technical issue by taking quantitative measure. The voting rule is according to the majority, but the majority, you take the majority of let the voters vote, then you look at the set of voters who voted A, itself, it's about 50% then pay. But this measure is quantitative, not rather than quantitative. This is what the other takeout that I took from this talk is that if the voters want to protect themselves from being manipulated, they can just vote randomly according to their posterior.
What do you mean, what, vote randomly?
If my posterior is 51%.
Your posterior, after you get the signal or?
After I get everything,
You get everything. Yeah.
I get the point where I vote, and then I just randomize with 51% I vote A, 49% I vote, and by that I just you cannot manipulate this you cannot manipulate it. And another idea which maybe is a little too far. Maybe it can explain why we see in many elections that the results are very close to the draw in many countries. In recent years, we see that I'm not sure I know how to do it, but maybe these kind of models can explain this pattern, because the parties want to convince you to vote slightly above 51%. To be, sure, certain with small probability, or sure that the others will be different. Maybe some. Maybe. שאני לא יודע איך בדיוק לעשות את זה, אולי זה יכול להסביר למה יש בהרבה בחירות תוצאה שקרובה לתקן. כשמישהו מנסה לעשות עליך מניפולציה, גורם לך להסתברות גבוהה להאמין שכנראה שקצת יותר נכון להצביע במפלגה אחת, או בטוח שלהצביע השנייה. כך הוא יכול לעשות את זה. האמונה שלך מראש הייתה האמונה שלך מראש הייתה חצי חצי, נגיד להסתברות גבוהה להאמין שקצת יותר.
בקיצור, הסיבה היא שיש הרבה משכנעים בזיין.
כולם עושים יותר מדי אנשים.
יש לי הערה הצגתית, אני כאילו מאוד אהבתי, אני לא יודע מה אתם משנים פה, אבל מאוד מאוד אהבתי.